So we could do this analysis. Basically, there's a temperature, fixed temperature, right, 200 degrees here, 200 degrees C. And you could do a resistance here. Like they can actually act like little resistors, and then you have a resistor for this material, and then a little resistor for this material. And then we'd have another resistor for the convection that happens between node 4 and node 5. And at 5, we have a fixed temperature of 30 degrees C. So between all these resistances, these different materials, different modes of heat transfer, there's a constant Q dot. So just like with an electrical circuit, there would be constant current through all these. There's a constant heat transfer rate through all these heat transfer modes, different resistances of either material or via the convection. So let's see if this Q dot holds true, that it's constant for all our cases. It's kind of our check here. All right, so if we start off with the Q dot between nodes 1 and 2, all right, that's conduction. So we got a K, A, and then we got our delta T, which we solve for, or the different T's, the different nodes, divided by L, the length of that element. All right, so let's see what we come up with. So for K, it's 0.08 watts per meter K. And we got area, we said, was 1 meter squared. And the delta T is the 200 degrees C, that was the boundary condition, minus what we solved for was that 162.3 degrees C. All that divided by the length, which was 0.05 meters. All right. So if we solve that guy out, we're going to get 60 watts. All right. So the question is, do we get 60 watts between our other two nodes? So let's go to the other end and look at convection. So if we look at Q dot between nodes 4 and 5, that's convection. So we got HA, and we got our delta T. So we got T4 minus T5. And the H is, that was, make sure I get that right, I think it was 40. Yeah, 40. So we got 40 watts per meter squared K. Area, again, is 1 meter squared. Temperature at node 4 was what we saw for 31.5 degrees C minus the 30 degrees C fixed for the fluid temperature. And hopefully you're going to see there I got the 40 times 31.5 minus 30, we get 1.5, and that's going to give us 60 watts. All right, so those guys being the same, we can be pretty confident the rest of the results are going to be good. Probably want to check those as well, but that's one way you can verify your results, at least of the thermal analysis. All right, so let's move on to a fluid mechanics example, right, to see the generalness of the stuff we just developed. Right? So we're looking at this fluid mechanics example using, again, linear elements. So we have laminar flow in a channel. It's Poisson's flow, so we have a pressure-driven flow. So you have an overall velocity profile, which actually looks kind of messed up. Probably shouldn't be like that. Now we got a height h between the two plates, and we have a width w in the z direction out of the screen. All right, so starting with the governing differential equation. All right, so we have some viscous effects, and we'll have the pressure gradient, which is driving the flow, which is helping the flow move. All that equal to 0. All right, so we got the velocity of the fluid is u, dynamic viscosity is mu, the pressure drop drives the flow, and the temperature on the channel surfaces in the fluid. Actually, we don't need that. It doesn't apply to the situation. Cross that off. So boundary conditions. So we got 2 for linear elements. So we have the velocity is 0, so no slip conditions at the bottom at y equals 0. And we have no slip at the top at y equal to h. So that looks good. So note that the governing equation is the same general form as the equation we dealt for heat transfer. All right, so we had our second derivative of the psi, respect to x times the coefficient, plus the second coefficient times psi plus third coefficient. All right, so in our case, psi is equal to u. Right, so we have the velocity. X is equal to y. we're changing in the y direction between the two plates. C1 is our mu, viscosity. C2, we actually don't have that term at all, it's 0. And then C3 is our pressure gradient, that's constant. All right, so the derivation we did for heat transfer, so we have the stiffness element, stiffness matrix for an element, and then we have the stiffness matrix for C1 and the stiffness for C2. All right, so for C1, all right, it's going to be our mu value. We're going to substitute in there. And for C2, we said C2 is 0. We actually don't have this term, so that term just goes away. All right, so the stiffness matrix that we have here is the viscosity over the length of our element and multiplied times our stiffness matrix that's been developed there. All right, so that's our flow resistance matrix. All right, so this was kind of its conductance before. In this case, it's a flow or the viscous effects here. From our force matrix, all right, forcing functions, we got C3 divided by L. C3 here is our pressure gradient, so we got the negative dP dx L over 2. And that's our flow forcing matrix. Kind of makes sense, right? The pressure gradient is what drives, what drives the flow. Right? So for fully developed laminar flow, we've talked about this in fluids, is that dP dx is a constant. Right? So as before, we're going to sum our global stiffness and force matrices, and solve for the global matrix equation. Right? To get global K values, and then ultimately we can solve for, this would be probably global U's, and then work backwards to our local U values. All right. So looking at our 1D model here, so again the setup here is a nice Poisson's flow. That one's a lot more symmetric there. All right, again it's a constant pressure gradient that's driving it, breaking up into 5 nodes and 4 elements. 0, no slip at the 2 elements, nodes 1 and 5, no slip there, so velocity is already declared to be 0. All right, so that would be the setup for the model, and you could follow through using the same process we did for the heat transfer problem. All right, so if we want to get mass flow rate in the channel, get the total mass flow rate, we'd sum up the mass flow rates for each element. And to get those guys, all right, so we sum them up. We would use the velocity we'd have for each element, the width out of the page, times the density, because again we're going for mass flow rate. And we're going to integrate that with respect to y from the node I to node j to solve for the m dot for that given element. So d is the density of the fluid, w is the channel width, and u is the element flow velocity. So with those we could calculate then the mass flow rate, total mass flow rate, by summing up all the mass flow rates we got from each element. All right. So looking at how we substitute that in for our velocity here, we got our shape function form. Again, we're using linear elements, so it's the shape function node I times the velocity at node I plus the shape function node j times the velocity at node j. And if we substitute those in and do the integration, we come up with just the average. That kind of makes sense because we got linear elements. The average of the velocity at either end of the element times rho times the width of the page times the length. That gives us the mass flow rate. All right, so hopefully that makes sense for that calculation there. Again, always you want to verify your answers. Right? So like we did with the heat transfer case, to some degree of certainty to make sure you can get a lot of nice values. Hey, the thing runs, but do they make sense? All right. So you can see lots of books for conservation of energy in elements to do that analysis. But again, the big kicker here is you want to make sure you're verifying your results. Exclamation points. Which makes me happy. All right, so hopefully you guys enjoyed the presentation. Again, if you have any questions, let me know in the comments below, and I hope you enjoyed it. Thanks.